Hello and welcome to this lecture on life contingencies. This is the overview of what we are looking at today. In many real life problems, we are interested in the time until an event occurs. So examples can be time until death, that is in mortality studies, time until a machine fails, reliability theory, or the time until a patient relapses in medical statistics. Our focus, of course, will be time until death. So all these problems involve modeling uncertain future time. If the events of the future can only be predicted, you cannot know for sure how things will span or turn out. However, there's still a need to model the future to be able to take some decisions today. So it's important for us to be able to model the future based on data that we have, information we have up till now. We use information from the past up to now to predict what could happen in the future. In statistics, we call this survival analysis. That is the time to event data. In actuarial science, survival analysis provides the math foundation for mortality modeling, life insurance evaluation, life annuity pricing, pension modeling, and so on. So, in example, like life insurance valuation, if you go to buy a life insurance product, you will be assessed. And then the insurer will predict how many years you are likely to live. And based on that prediction, using established probabilities, they predict using established probabilities. So based on that prediction, they will determine how much premiums you should pay to them and how much sum assured will pay to you when you die. So we look at the future lifetime random variable. Many insurance policies provide benefits upon the death of the policyholder. However, the policyholder's date of death, we don't know. So the insurer cannot determine exactly when the benefits will be paid. Okay. So we have a model of human mortality that is used to calculate the probabilities of death at specific ages. Now, this model of human mortality, we call it life tables. Yes. And that's a video you're going to be watching on your own. I will send the link over to you. So let's take a person age X to represent a life aged X, where X is greater than or equal to 0. Now, death for this individual can occur at any age that is greater than 0. So it can occur now or it can occur later. We define the future lifetime of X, which is modeled as a continuous random variable given as Tx. So Tx represents, I'm currently age X. How many more years do I have to live? That is Tx, and I don't know it. So Tx stands for number of years, but X here stands for age. And we denote it X, this T by the X here to show that, this small X here, to show that we are looking at the future lifetime of a person who is age X. Therefore, the random variable X plus Tx represent the age at death of the individual. Because this X here is your age and this TX here is your future lifetime. How many more years do you have? So if you add your current age to the number of years more you have, it becomes the age at which you die. Let's look at the lifetime distribution function. We have fxt being given as probability of tx being less than or equal to t. So how do we define this? Fxt is a probability that an individual age x dies within t years. Now, fxt is known as a lifetime distribution from age x. We also have a survival function, sxt, which is equal to 1 minus fxt, and it's given as the probability that a future lifetime of a person age x is more than t, which says that the probability that a person age x will live beyond t years, or you will live at least TS. We call it the survival function. So consider a person, we want to transition from birth to the current age. Consider a person age X with a future lifetime Tx and an age at death random variable X plus Tx. All right. Oh. So once again, consider a person age X with a future lifetime Tx and an age at death random variable X plus Tx. If the person survives to age X, then the initial lifetime T naught represents the future lifetime of a newborn. This zero here represents age 0, and age 0 is for a newborn. So their initial lifetime T naught is greater than X because the person has already survived to age X. So we want to understand, for a person who has survived to age X, how do we understand their future lifetime from the perspective of a newborn? As to from the person, you want to go back to when they were newborn, trying to understand their future lifetime, given that they are currently age X. So their future lifetime Tx represents the remaining lifetime. Here is an important relationship. The probability that Tx is less than or equal to T, or the probability that the future lifetime of a person age X is less than or equal to T, or the probability the person age X dies before the next T years or dies within the next T years is given as the probability that T naught is less than or equal to X plus T, given that T naught is greater than X. Okay? So from the newborn perspective, we are saying that this is the probability that a newborn will die within the next X plus T, given that a newborn has already survived beyond age X. So if this is a conditional probability, then the lifetime distribution fxt is equal to, let me write this one up here. Okay, we have probability of Tx being less than or equal to T is given as a probability of T naught being less than or equal to X plus T, given that the person, the newborn, has already survived age X. Per the rule of conditional probability, we have the probability of A given B is equal to probability of A intersection B all over probability of B. If this is the case, then from this side, we know that this is like the B of the conditional probability, and this side is the A, okay? So you have probability that T naught is greater than X being in the denominator. So we have it here, S naught X, which is the probability that T naught is greater than X. S naught X is the probability that T naught is greater than X. All right. All right, so we have the denominator sorted. Now the numerator is saying the probability that T naught is less than or equal to X plus T. That is the probability that the newborn dies in the next X plus T years. This is going to be this is F naught X plus T. That is the probability that the newborn dies in the X plus T, the next X plus T years. But you must take away the possibility that a newborn will die in the next X years, because we've established that a newborn has already survived to age X. So you take away the probability that a newborn dies before age X, which is F naught X. That is why we had the numerator as F naught X plus T minus F naught X. As for the denominator, we have already established it. We also have the survival function. Sxt equals S naught X plus T all over S naught X. So this is the probability. Sxt here is read as the probability that a person age X survives T more years. And that is equal to the probability that a newborn will survive beyond X plus T, given that he has already survived beyond X, which is what we have here. So the survival probability from age X to X plus T is expressed as the probability of surviving to age X from birth and the probability of surviving from age for surviving further to age X plus T, given that you have already survived to age X. So we have an example here, splitting survival probabilities. We have Sxt plus U, which is the probability that a person age X has survived T plus U years. And that is equal to the probability that a person age X has survived T years. And then now that he is age X plus T has survived U years. So example calculation is, suppose S naught X is equal to e to the power minus 0.05x, a simple exponential survival model. We have compute S4010. That is, find the probability that a person age 40 survives T more years. So we have S4010 being equal to S naught 40 plus 10 all over S naught 40, taken from this relationship from the previous pages. From the previous pages, we had Sxt equals S naught X plus T all over S naught T. No, S naught X, sorry. All over S naught X. Okay. So we have this S naught X plus T all over S naught X. So I just fix in X is 40. Here, X is 40, T is 10. So I fix in the values S naught 40 plus 10 all over S naught 40. Then wherever I see, according to the function, S naught X equals this. So whatever is in the bracket, I replace it with the X. I replace the X by it. So we have e to the power minus 0.05. The bracket here is 40 plus 10, which is 50. So I have here 50, and then here is 40. Simplify to get 0.6065. Whilst I explain what these notations mean, do well to write it down also. So you write it. TPX means probability that this, that. SXT means probability, so that you get used to them. Now, these are some properties of the survival function SXT that allows you to define a valid lifetime distribution. The first condition is that SX naught is equal to 1. That is, a person who is currently age X survives 0 years with probability 1. If you are currently age X, the probability that you survive 0 more years, it means that that's it. You are currently age X. So the probability of you being, you are currently age X. What is the probability of you being X like now? The probability is 1 because you've already attained the age. Also, number 2, the limit as t approaches infinity of sxt is equal to 0. So if you are currently age X, what is the probability that you will live infinity more years? It's 0 because everybody will eventually die. Nobody will live infinity. So the probability of a person currently is living infinity more years is 0. You cannot live infinity years. So it is an impossible probability. It's an impossible event. Yes, because nobody can live to infinity. That is why it's equal to 0. And then also SXT is non-increasing. As you grow, the probability of your survival is decreasing. So for somebody who is 90 years old, has a much lower probability of survival than somebody who is 10 years old, all things being equal. All right. So as you are aging, your probability of survival is also decreasing. So we see that SXT is non-increasing. It does not increase. All right. Now here is these are some illustrations to verify that SXT to verify the properties of SXT. Now we want to look at actuarial notations. The notations we have used earlier have been SXT, FXT, and this one, the PDF, in standard statistics. But actuarial science has its own specialized um, notations, and I want to introduce you to that. We have TPX, which is the actuarial notation for SXT. We have TQS, which is the actuarial notation for FXT. And then we have U bar TQX, which is the actuarial notation for SXU minus SXU plus T. Now, these three actuarial notations are defined on the next page. Okay, so this one, and this one is defined on the next page. So let's get into that. Great. So here are the interpretations. TPX is the probability that a live age X survives to at least age X plus T. And TQX is the probability that a live age X dies before age X plus T. And U bar TQX, that is this one, is the probability that a live age X survives U years and then dies in the next T years. The probability that the person age X survives U years, that is on the left side of the bar, and then dies in the next T years. We call this a deferred mortality probability because it represents death after a deferred period. So when T is equal to 1, TPX is written as just PX because there's a 1 here we usually do not write. Okay. There's a 1 here we mostly do not write. So TPX is the probability of surviving 1 year. And then TQX becomes QX when T is equal to 1. That is the probability of dying within 1 year. So whenever you see just QX or PX without anything hitting it, means that it is the probability of surviving within the next 1 year or dying within the next 1 year. All right. Here are also some key relationships you should take note of. From the definitions and error results, the following relationships hold. TPX plus TQX is equal to 1. If you are currently age X, the probability that you survive 10 more years plus the probability that you die within the next 2 years is 1. Because within the next 2 years, you either survive or you die. So if you add these two probabilities, we have 1. We also have the deferred mortality probability, which is U bar TQX, and it's equal to. So this is the probability that a person age X survives U years and dies within the next years. So we are saying that it is a probability that a person age X survives U years. Take away the possibility of the person age X surviving U plus T years, because the person will not survive U plus T years. So you must take out this possibility that he will survive U plus T, and that will give you the probability that the person age X survives U years but dies in the next years. We also have a compound survival probability, which is the probability that person age X survives T plus U years. And that is equal to the probability that a person age X survives T years, and then now that he is age X plus T, survives U more years. And remember, probability, once you see end, that is multiplication. So here are some examples to try. Example 1. We have the probability of survival. So let 2p30 be equal to 0.85, and then 1p32 be equal to 0.9. Okay, so to solve this example, we want to find 3p30. That is what we want to attempt to find, okay? So what is find? No, let me write it here. I will say calculate 3p30. Now, this 3p30 is the probability that a person age 30 lives for 3 more years or lives beyond the next 3 years. Okay, so 3p30 then can also be written as a person age 30 living for 2 more years. And then now he's at age 32 because he has lived for 2 more years. Now that she's at age 32, lives for an extra 1 year. Now we already have 2p30 is given as 0.85, so we put it here. Then 1p32 is given as 0.9, we put it here. Then we multiply to get our answer. So therefore, the probability that life age 30 survives 3 years is 76.5%. Now here's example 2. Deferred mortality probability. So suppose we have 2p30 given as 0.85 and then 4p30 given as 0.7. Then the deferred mortality probability is given as, so what we want to find is, you want to calculate, sure. Calculate 2 bar 2 kill 30. So to calculate this, we have to use the relationship kill 30, 2 bar 2 kill 30 is equal to 2p30 minus 4p30. What is this? This is the probability. Look at this side, the left-hand side here. It's the probability that a person age 30 survives 2 more years and then dies in the next 2 years. So this is equal to the probability that a person age 30 survives 2 more years minus the probability that a person age 30 survives 4 more years, because she will not survive 4 more years. After she has survived 2 years, she will die in the next 2 years. So that possibility of the person age 30 surviving the next for extra 2 years, which is the next 4 years in total, is we take it out of this. And we already have 2p30 and 4p30, so we have 0.85 minus 0.7 from here. And then we have the answer as 0.15. So we can attempt to plot TPS and TQX and see how they look like. This is how TPS and TQX looks like. Recall that we said that the TPX is a non-increasing. So you can see that it is gradually decreasing. Okay, as you age, the probability of your survival reduces. And then as you age, the probability of your death increases gradually. It's a very slight exponential curve. Now for this curve also, we see that the blue line represents the probability of a person age X living T more years. And then the green line represents the probability of a person age X living T plus U more years. Think about it. This person in green, you're looking at the probability of the person living older. So um, the blue line represents the probability of a person age, let's say 30, living 5 more years. And then the green is the person age 30, living 10 more years. The probability of a person age 30 living 5 more years is expected to be bigger than the probability of a person age 30 living 10 more years. Because the probability of you living to age 35 will be bigger than the probability of you living to age 40. That is why you see that this is for the blue line. These probabilities are bigger than these probabilities. So if you look at year 4, for example, the blue line has a bigger probability than the green line. Okay. Because for the blue line, we are checking probability of you living in the next um closer year. But for the green line, we are checking the probability of you living in a much farther year. And of course, once we're estimating farther, you, um, you are more likely to live sooner than later. Yeah, so that is how best I can say it. Now we want to look at this simple concept. We call it the Curtis future lifetime. In many insurance applications, we are interested in the Curtis future lifetime of an individual in addition to their exact future lifetime. So we define TX as the future lifetime random variable, and TX can fall on any time. TX doesn't fall on your birthdays only. People die at any time. So you may be 95 years, you turn 95 in February, and then by September you have died. So you notice that you have died at probably age 95.5. So you have died at age 95.5. Therefore, your X plus TX is, given that you were age 30 and you lived 65.5 more years, you are currently age 95.5. Okay, this is X, is X, this is TX, this is X plus TX. Therefore, your KX is equal to the floor, we call it the floor of TX. That is the integer part of TX. In this case, TX is 65.5. So your KX is equal to 65. It's not a rounding up. You don't round up. You take just the integer parts of TX. So you ignore the decimals. You just take the integer parts. So you will consider a KX to be 65 in this case.